I was at UCLA studying physics. I've always been interested in the foundations of physics, the deepest aspects of nature. And obviously, quantum mechanics is at the most foundational level. And I got recruited while at UCLA by a place called TRW. A professor, some people were interested in me. I did some work at UCLA as an undergraduate, published some papers as a junior college. And that got the attention of some people at TRW, and notably a kind of famous guy, Arnold Silver. He was the co-inventor of the SQUID, which is an acronym standing for Superconducting Quantum Interference Device. The SQUID's an interesting object because it's actually the basis of the quantum computer we're working on, and others in the superconducting community. And it's an object that was predicted historically to be the first object to demonstrate weird quantum phenomenon at macroscopic scales, something you can see with the naked eye. My first job out of college was with the co-inventor of the device, which would eventually be the device to show macroscopic quantum effects. And so when I got hired into this group, what the group was working on was quantum electronics, superconducting electronics. So that had the promise of operating much, much faster, 1,000 times faster, with 1,000 times less energy consumption, right? And this would be able to extend Moore's law well into the future and solve problems that would otherwise be beyond the pale of what CMOS could do, right? So that's what this group did. And so when I got hired, my initial attraction to that whole field was, one, they offered me a job. Two, I was working with some very well-known people who had done some brilliant work. And three, it was quantum mechanics on a tabletop. So we were building this technology, and we had the most advanced processing capability in the world at the time, and I learned a ton of stuff. I learned how to build superconducting electronics from the ground up. I learned all kinds of cool physics. And what I used to do for fun, I always was trying to educate myself about new things going on in the field. Caltech had a series of free lectures, the Beckman lectures. And in 1997, I think it was, there was a lecture entitled Quantum Computing by a guy named John Preskill, a very well-known and respected theoretical physicist. And I knew what quantum mechanics was, I knew what computing was, but I didn't know what they had to do with each other. It wasn't the buzzword that it is today. So I went to that lecture, and I took Arnold Silver, the inventor of the SQUID, with me, and a couple other people from TRW, and we went to this lecture, and it blew my mind. Sort of this Alice in Wonderland stuff. I mean, one interpretation for quantum mechanics is that there's parallel universes, right? And that when you look at the quantum mechanical equations and they tell you that all these disparate physical phenomena are happening at the same time, like the same physical object being in many places at once, or living out many possibilities simultaneously, that kind of thing. The idea is that, the basic idea behind quantum computing is if I can have single objects live out many possibilities simultaneously, what if I could have computing elements, the same physical hardware, behave as if it was many, many pieces of hardware, or one processor operating like it's an incredible number of processors operating in parallel, doing different parts of a very difficult problem. But the thing is, the way parallel process is done today, you actually have to build physically new processors, right? But what if one processor could behave like 10 to the 500th processors operating in parallel? It staggers the mind, right? So he was giving this talk, and David Deutsch, who was sort of the progenitor of quantum computing, he's a big fan of the many worlds interpretation of quantum mechanics. He came up with this idea by saying, what if you could access all these parallel realities and do different parts of a complex computation in them simultaneously, and somehow extract information from the multiverse, right? This was an amazing thing. You're harnessing a whole new resource in nature. You're technologically accessing these parallel universes, and this is something that human beings have not been able to do, heretofore. So I went to this lecture, was kind of had my mind blown, and at that moment decided that's what I'm going to do. And beyond that, I said I'm already working with materials, superconductors, and building superconducting circuits and objects that behave quantum mechanically at a macroscopic scale. So when I walked out of that lecture, I thought, he's talking about doing quantum computing. He talked about doing it with ions, nuclear magnetic resonance, photons. And when I walked out, I thought, well, yeah, those are all microscopic systems. And it's very difficult to access and control and manipulate and engineer microscopic systems. But superconducting circuits are macroscopic. If you could get, and they already demonstrate a lot of the requisite behavior, if you could build quantum computing elements out of superconducting circuits, you could have a macroscopic technology where it's already known how to build large-scale versions of that. So I got very excited about that idea. So I proposed it to Arnold. And at the time he said, you seem to really be into this. I like your idea. I'll pay you 1 day a week to think about it. So 1 day out of a week, and give me a lecture every couple of weeks about what you're thinking. So that's how that started. And in the course of that, over the next 2 years, I read every paper I could find on the internet, spending late nights at the UCLA library. And it was interesting because what I discovered was this amazing story that was going on. This idea, why is it if the microscopic world behaves in this Alice in Wonderland-like way, and we're made out of those atomic constituents, why don't we behave that way? Right? This was a big quandary. Why does quantum mechanics not work when you get to a certain scale? And yet we saw signatures of quantum mechanics in things like superconductors at large scales. So this is very intriguing. So when I started looking into this field, I found a paper at UCLA by a Nobel Prize winning physicist, Tony Leggett. And what he predicted in this paper was if you wanted to see a Schrodinger's cat, now not actually a cat, but if you wanted to see a macroscopic object, very, very large compared to the scale of atoms, that would be, you could put into two states simultaneously, he predicted it would be a squid. And I was working for the guy who invented it, and I was in a group where we built them routinely. I went to the UCLA library, I read that paper, and I went, wow. This was 1998 and 9, I was reading all these papers. So for 2 years, I read papers, I reported to Arnold Silver about my ideas about how to maybe pursue this field, about how we might leverage what was going on in superconducting electronics at TRW. And then I went in 2000, I went to a conference. It's called the ASC, the Applied Superconductivity Conference. And at that conference, there was a group in New York, SUNY, so State University of New York in Stony Brook. And a group, a guy, Jonathan Friedman and Jim Lukens, succeeded in making the world's first Schrodinger's cat. They put a squid in a macroscopic superposition of two mutually exclusive states, and it was in the New York Times. And I had been reading for 2 years, anticipating the day when someone would finally get to superposition. So they had tunneling, they had energy. And I went to that conference and I saw his poster, and I hadn't seen the New York Times yet. And it was like, my God, there it is. And what he had done, the simple way of explaining it is, if you take a ring of metal, it's just a ring of metal. You can look at the periodic table, niobium. It's a pretty common material. But when you put that material at low temperature, in liquid helium kind of thing, it becomes a superconductor and has these macroscopic quantum properties. Well, what they had done is taking it to very low temperatures, millikelvin, and essentially put this in a very strange state of affairs. They had this ring of metal. There's a detail, something called a Josephson junction in there. But they ran a current clockwise, right? All the current was going clockwise. It's important. All the current's going clockwise. And all the current was going counterclockwise simultaneously. So they did an experiment that demonstrated this. So that's rather like you being at the velodrome on your bike and going clockwise and counterclockwise simultaneously, one individual, right? It's that kind of crazy. And I said, there it is. And so the New York Times article was Schrodinger's cat lives. So quantum mechanics does apply on the macroscopic scale. It's universal. And the reason we don't normally see it is because of all of these interactions with the external environment with this object. They had isolated the object sufficiently and it had the requisite properties to demonstrate the full-blown quantum mechanical effects at macroscopic scales. So this was, to me, a revolutionary thing. And I said, there it is. That's my quantum bit. Because there's lots of ways that you can represent zeros and ones. It could be the light switch, up and down. It could be a transistor on and off. And in this case, current going one way could be a 0. Current going the other way could be a 1. But you could put it in a state of being a 0 and 1 simultaneously. And that's a quantum bit. That's your qubit. And I said, that's the basis of the quantum computer I want to build. And I just hatched this idea. I thought, what if you could get some of the best researchers in the field, like the group that demonstrated this, get them well-funded, collaborate with a group like TRW that had this industrial might behind it to build devices, do experiments, microwave engineering, all of that stuff, material science, because the materials, there's fluctuations in materials that make the quantum effects go away, but we had a whole material science division. So I said, what if we were to take that industrial might, kind of like when they ramped up the Manhattan Project with all the isotope separation, and then couple it with some of the best physicists in the field. And then beyond that, I said, you also have to look at applications. You have to look at the mathematics that underlies the quantum information processing. And those 2 years of reading, I had surveyed the entire field. I said, here are these physicists who are doing some great stuff. Here's TRW that has all this industrial might. Here's some guys who are doing really great algorithmic work. So I hatched this idea for a quantum computing Manhattan Project. 2 weeks later to the day, a researcher at the Colorado branch of TRW randomly called our group. DARPA has just issued a BAA, which stands for Broad Area Announcement, for where they are putting aside $100 million for projects in quantum computing. I said, I have this little mini Manhattan project. I'm going to figure out, I'm going to say how many people, what resources, how many experiments. I figured all that stuff out. I wrote milestones and all that. And I said, what would it take to do something substantive in 5 years? Minimum. And even then I was underestimating. And I came up with about $10 million, 5 years. And they said, you'll never win that. And I said, that's what I'm going to go for. So I wrote a very ambitious proposal. And in the meantime, I went and visited all these scientists who would be on the team and got to know their teams and the research they were doing and put all the stuff in the proposal about what we would do, organized all the efforts so it would interleave in the right way with all the right stuff, and sent it in. And I thought, well, if nothing else, I got to meet all these really great, smart, interesting people, and been exposed to this field, and I know it's maybe improbable. 2 months later, a letter arrived. You've been selected for your project. You won a $10 million DARPA project in quantum computing. And I was principal investigator. And that's how it started. So that was my DARPA project. Now, the DREAM project, very quickly, I came to realize that when working on government projects, tremendous bureaucracy, slow, working with academic groups that aren't used to working on a Manhattan project. They were disparate groups in different locations. They had teaching responsibilities. They had, that kind of thing. The culture wasn't the right kind of culture. I started realizing I need to co-locate these people. They have to be dedicated to this and this only. They have to be used to hitting milestones. And one of the first things that I knew wouldn't work is I said, well, okay, here's $10 million, put it in a bank account, and then based on the milestones that we've agreed to, I will pass out the money. What they did instead was they said, oh, here's how much money you had allocated to the Sunni group and this group and that group, and they were giving it to them individually, and I said, you just ruined the team, because while they'll be nice and collaborative with me, unless there's somebody who's handing out the money and there are deliverables and there, all of that, I could see the writing on the wall. I said, this is not going to happen. Well, I was giving one of these talks to the broader community. Some people, I pissed them off. They thought I was being critical. I thought there was great physics going on, but I said, this activity, the way it's organized, will never build a quantum computer. And shortly after that, I was reading the book on Craig Venter and how he mapped the human genome. So there was this big international project, right? It's going to take a decade and billions of dollars. And he said, I'll do it in 3 years for $300 million. And he did, right? And there's caveats there, but nevertheless, I looked at that same thing. And I said, that's another model of a more recent variety. And I was also directly involved with a friend of mine who left TRW, built a company, and built a microfluidics technology, so this microscopic, chemistry lab on a chip kind of thing. Problems that had existed for decades, he solved in months. And I saw how he did it, rapid prototyping, lots of experiments per unit time, kind of a similar philosophy to what I had. So I was at a conference, and I was giving a talk to this effect, like, here are my impressions about what we need to change to make this happen as a technology. One of the people in the audience was Colin Williams. He was a pretty prominent guy. He used to work with Stephen Hawking, in cosmology in Cambridge. Got very interested in artificial intelligence. Ended up being he was a professor at Stanford. He wrote the first textbook on quantum computing. The textbook that Geordie Rose read that got him interested in the field. Now, at the time, Geordie Rose, who was doing this intellectual property company, he had a few people. The idea was, if somehow I could shuttle venture capital to groups that had promising sort of models for quantum computing or hardware implementations, because I'm a theoretical physicist and this group I'm working with understands that stuff, we can be this kind of the people between the resources and the people who are doing the research, the experimental research. So they said we would provide direction, technical direction, theoretical support, money, equipment, whatever, and assess the various models of quantum computing, shuttle money and resources to the best groups doing what we think are the best ideas, in exchange for which we would get intellectual property. And then we build this big patent portfolio. And when quantum computing comes of age, and we have all this intellectual property, we clean up. That was the business model. That was the 1999 D-Wave that started up. And he was doing that for a number of years and came to the conclusion, the same conclusion I did for different reasons, that this disparate amalgam of researchers, distributed researchers, will never build a quantum computer. There's not enough cohesiveness, culture, drive, ambition, whatever. So he was getting frustrated. And this was I think he was about 5 years into the project. Because it was about 2004. I gave this lecture. I won my DARPA contract in 2001, worked on it for 3 years. Cool science, but I was dismayed at how the pace of things and where it would go. I gave this talk. So Colin Williams, whose book I'd also read, approaches me after this lecture and says, we should start a company. Now, I said to Colin, no offense, you're a theoretical physicist, don't know how to start a business. I don't either. I think I know how to put together a good technical project and run it and inspire people and all that. But raising money and venture capital, I don't know anything about that. Now, we were sitting at Stanford late at night in a little cubbyhole, overlooking some nice garden. And he said to me, well, there is this guy, Geordie Rose, in Canada. And he said, this guy raised $20 million. And that was the moment where I said, aha. That was my next aha moment. I said, doesn't it make more sense for us to team with the guy who's already raised the money because you think that my Manhattan Project's the right way to proceed, and he has the money. And how about that? So eventually he thought, well, it'd be nice to own more of the company, but maybe that's a good idea. So he wrote a very nice letter of introduction to Geordi saying, if you want to build a quantum computer, you should talk to this Eric guy. I think he has the plan to do it. And vice versa, sent me a nice letter about Geordi, introduced us. And this was the difference I noticed with Geordi. Oftentimes you'll meet someone, have a conversation, they'll have action items. Oh, let's meet in a month and have lunch and discuss. So Geordi got that letter and I got a call the next day. He was in France with this group in Saclay. They was actually doing some good work. And he said, I hear you have a plan to build a quantum computer. I said, yep. And he said, I'm in France. And I thought he would say, maybe we'll meet in a couple of weeks, or could you come to Vancouver? And he said, I'm going to buy a plane ticket. I'll see you tomorrow. I was at TRW, and Geordi showed up. I remember picking him up at the, he was at a little hotel by the airport, and we didn't know what each other looked like, but somehow I think Colin told him I was a rock climber, and he said something about Geordi being a wrestler in the Olympics or something. So I showed up in this little hotel, and I see a guy who didn't look like a physicist, this big bulking guy, and I said, the wrestler. He said, the climber. I took my mini Manhattan Project proposal and said, this is what I would do. This is what I wanted to do in this government contract, but because of all this, disparate labs and conflicting cultures and all of that. And he said, here's my business model. What do you think of it? I said, it'll never work. And he asked me why. And I gave him a whole set of reasons. And he agreed with them all. He said, that's exactly been my experience the last 5 years. What would you do? So for 3 days, I told him what I would do. Who I would hire, how you hire a team. It has to be applications driven. Like, even though it was at an early stage, like, what are you going to do with it if you have it? You have to start thinking about it, because the applications define the architecture, define the device requirements, right? So I said, let's start from a processor, not from individual elements. What is this thing going to do? And then let's ask ourselves, is there a model that's easier to achieve? So I had this idea, like, there's this continuum of quantum effects. Some are easier to achieve than others. Could we build some device that didn't have the full palette of quantum mechanical effects, but still did something useful on path to the dream machine? We had this evolutionary idea for quantum computing. And then, after 3 days, he said, let's make your vision into the new vision for D-Wave. This is phase 2. Let's go from an IP company to a technology development company, and let's do what you just told me. So I said, and he said, I got $20 million, hire your dream team, let's go. I never had anybody say that to me before. So it's like, wow. So I decided to take him up on it. I took a little time at first, just doing kind of part-time, and then pulled the trigger and said, okay. Our first dilution refrigerator was something I bought on our Quist project and talked to DARPA and got them to transfer it to us. We paid for it, but so instead of 18 months, we were online in a month. Recommended a group of people, so there were a bunch of world experts, superconductivity circuit designers, and physicists from TRW who worked with me before, and I hired them. I hired some of the best people in the world from TRW. We hired a guy that he and I liked from Maryland, who had shown the first quantum entanglement in superconducting devices. And then I started hiring like the core technical team, and then he had the theoretical physicists that he had before. And we put the team together. The next big hurdle was, how are we going to build things? We need a superconducting fab. This brought up another issue. This is about doing things in a different way. The conventional wisdom for a long time in the superconducting community was that, well, you can't get like the semiconductor community guys to build superconducting, circuits. All of the superconducting groups in the world that built superconducting circuits were usually physicists, with some technicians or something They would build their own clean room. They would buy a few pieces of equipment. The problem with that is it was never done in a production facility, and it was like, little wafers, one wafer at a time. And I looked at that when I was at TRW, because I did that too. I learned how to build superconducting circuits from the ground up at TRW because I had to for my research. And I said, doesn't it make more sense to teach people who make 1 billion devices on a chip how to do superconducting stuff? It's not exotic to build. The physics is exotic at low temperature, but it's not that exotic to build. So very long story short, myself and Jeremy Hilton, who you've met, the VP, we searched the world for a semiconductor world-class kind of environment, like an Intel environment that was willing to do R&D, smaller volumes and different materials, and landed here at this facility. And I taught semiconductor guys all about superconducting stuff. I didn't hire superconducting people. I hired semiconducting people, and some best in class who were responsible for 65 nanometer technology. And that became the D-Wave team. I put a deal together with this place in Silicon Valley and leveraged the capability here. And in 2.5 to 3 years, we bypassed the world capability in superconducting circuits that had been building for 40 years. And I said, this is the Craig Venter Manhattan Project. It's like, because we had to, because you can exist in these other groups. They get government funded over the years. They never get past a certain place, but it's okay. You keep getting this government money. In our case, if we couldn't build a process that exceeded everything in the world in a couple of years, we were out of business. So we did. So we had to get creative. So came to Silicon Valley, taught semiconductor people how to do superconducting stuff, and we bypassed all the capability in the world in a couple of years. So, and that kind of brings us to where we are today. We have, and in the interim, we have 70 people in Vancouver, a team at JPL, which still does R&D and material science for us, world-class superconducting group here, and in the meantime raised $80 or $90 million, right, which was bigger than the entire U.S. budget for the. So it's like it worked out.